All right, this next section, the next chapter, chapter 6, we begin looking at some applications of the integral, whether a definite integral most likely, but just applications of integration in general. So the most notable application, first and foremost, is the geometric interpretation of a definite integral, which is the area between the graph of that function and the x-axis, where we treat areas that are above the x-axis as positive areas, and areas that are directed beneath or below the x-axis as having a negative area. So for one application, we can think of determining, the area between two curves. So if we focus on these three diagrams, working left to right, we can see how we can obtain the area between these two curves, the graphs of f and g. So in this first picture here, if we take a look at the area under the graph of f from A to B, so I'm going to draw this in a similar, semi-similar color. So this area here, that would be, let's actually draw the axis too, so that's all nice and neat and put together. So this is the area underneath the graph of f. So this is the antiderivative, the indefinite integral from a to b of f of x dx. Whereas I'll do this in red, this portion here that is the integral from a to b of g of x dx. So of course, if we take this larger area and we subtract the smaller area, we would be left with that, the portion that is not covered. So if we go ahead and line these two up as nicely as I can, it looks like what's left over is this petal, like flower petal kind of looking thing. And that right there in black, that area would be the difference in these two integrals. Specifically, we would take the area of the larger function, the top function, if you think of these two as who's on top, who's on bottom, f is on top, g is on the bottom, so we would do the top function minus the bottom function. Or, written in a nicer, more compact way, we can, since we're integrating over the same bounds, we can just write this as integral from a to b, f of x minus g of x dx. And that's great, and this is the formula you'll see in textbooks, but to me this is not really great because oftentimes students, as you're learning math and getting used to these formulas and how calculus is commonly communicated, sometimes we can latch on to the letters f and g and somehow impart more importance and significance to them than they actually should have. So for instance here, it's not really important which one we call f and which one we call g. I could make this formula a little bit less formal but more helpful, and that would be, I would modify this to say something like, let's go ahead and just say this is really better to think about this as top function minus bottom function. That's really, to me, a lot better. Okay. And on this page, we've got a whole bunch of different, we've got a theorem. We talk about what it means to be vertically simple, which is an idea that will show up again in Calc 3. So it is very important and useful to think about what it means for something to be considered vertically simple. Essentially, what vertically simple means is that in your area, the region that you're considering, whichever function is above the other, that function is always above the other one, or touching. They never swap. So if we go back to the previous page and we take a look at the graph of just these two functions, so let's look over here at the rightmost graph, all the way on the right. If I draw a vertical line somewhere between A and B, so let's only focus between A and B. Here, I just select a random x value and I draw a vertical line. So here we notice that f is on top, g is on the bottom. Now, if I move this x value somewhere else within our region A to B and I draw a vertical line there, again, f is on top, g is on bottom. And it doesn't actually matter where I draw this vertical line. No matter where I draw it, I always see that f is above g. However, if our region was not just A ending at B, but maybe A to this x value, something a little bit larger than B, it's like right about here, then we do see that G and F swap positions. So this formula of top minus bottom only is valid in these subregions where the one graph is always above the other graph. If you wanted to know this additional area here, so this area added to this little area, then we couldn't keep the same order of subtraction, because from A to B, F is on top, G is on the bottom, but from x equals B to, I don't know, let's just say that this value here is, I'll call that x equals c. So if we wanted this full area here, then we would have to do, we'd have to do integral a to b f of x minus g of x, top minus bottom, plus we'd have to do the integral from b to c of g minus f, because which function was above the other swapped. This order of above versus below, who's on top, who's on bottom, that changes. So we would say that this full region here, this full region is not vertically simple because they flip at some point. There is some point where the functions flip. A region is vertically simple if they don't flip. So this portion is vertically simple, and this portion is vertically simple, but if we glue them together and think of this as a single large region, that larger, more general region is not vertically simple. So essentially what this theorem, or what this idea is talking about, is if your region's not vertically simple, then that means you're going to have more than one integral to get the area. So for instance, down here, in remark number 2, if we consider this full thing from negative pi all the way to pi as one big region, it is clearly not vertically simple because we've got some problematic areas here. It's where they intersect and they flip. So here it flips. Here at pi over 4 they flip. So we really kind of split this up into 3 regions. We've got the portion from negative pi to negative 3 pi over 4. The region, so I'll call that region 1. And then we've got the region from negative 3 pi over 4 all the way to pi over 4. So call that region 2. And then we have the region from pi over 4 to pi, call that region 3. So for region 1, we have let's see, let's figure this out. This is f right here. So f is on the bottom, g is on top. So for region 1, this would be something like g minus f dx. For region 2, this would be something like f minus g dx. And for region 3, this would be g's on top, so g minus f dx. And of course, we'd have to integrate over the correct bound. So negative pi to negative 3 pi over 4. Pick up where we left off. Negative 3 pi over 4 to pi over 4. Pick up where we left off, so pi over 4 all the way to pi. And that's precisely what we have over there. It's also important to know that just because two graphs intersect, that doesn't necessarily mean that you are going to need to have more than one integral. It really matters not that they touch, but that they actually switch who is beneath or above the other. Being equal to one another is not terrible. So for instance, you could have something like, I'll just draw a hypothetical graph here. So here's some axes, and I'm going to draw the graph of, let's say, I don't know, I'm going to make this up. Something like that. And then maybe I've got another graph, so let's call that graph F, and then I will draw something in blue, and I will have this be, let's say I've got comes down, touches, just like that. Let's call that G. So in this case of these two very strange looking functions, if I wanted to know this area here, so this area, so this strange red area, it would still be it would be G minus F. I'm going to put F down here. Because although they touch, they never actually swap who's above or above the other. They stay the order that they are. They might meet, but then they go back to where they were, one above the other. So this is an example where just because they intersect doesn't mean you need one integral. We could actually figure out this. So if I call this x value here where they meet, let's call this x equals a, and I call this point here where they meet x equals b, then this area in red, let's call it a, would be the integral from a to b of the blue function g minus the black function f. So there we go.